Right. Hello, YouTube. Hello, everybody. Hello, Ben. How are you?
I'm well. How are you, Bill?
Hanging
Well, I
in
was
there.
saying
Had
I
some
have a sore back.
tornadoes the last couple days, but we're surviving. Lots of rain out here in New Jersey.
At least you don't have a water shortage right now, right?
Right, right. I mean, it's the same problems, only different variables for everybody, right? We're too much water, and you guys. My sister lives in Los Angeles, and it's fire season again already.
I have some good news that relate to weather.
Okay.
Um, Other years around San Diego this time of year, we've had pretty nasty brush fires, bushfires we
Right.
call them in Australia. This year,
Right.
it's been more temperate, and we actually had quite a large couple of thunderstorms over the last weekend, and they cooled everything down. The ground got a good soaking,
Good.
um,
Good.
but but I want to say it was Monday or Tuesday morning this week at 5 a.m. Big thunderstorm squall over our house here in South Escondido, and there was a massive lightning strike. I was just getting up because it was time to get up and start getting ready for the day. And this thing lit up the whole house, just the whole house like day. And it was very close because there was only about a second delay
Right.
between
Right.
flash and the loud sound. So it was very close to here, probably just up on the hill nearby. And instantly all the power went out.
Right. Right.
And I know it was Tuesday morning because I was actually going out um, Tuesday morning, and so I thought, oh great, I wonder how long it'll be before they flip the breaker back on. And so I went out. I was out for about an hour and a half, and then I got home, and power was restored. And I'm like, cool, I'll just get on with the day. And the storm was over, and no internet. I'm like,
Right.
oh crap. And the
Right.
router was on, Wi-Fi was all working, no internet. So I'm like, there's a problem. And the D slam, I'm on ADSL. The D slam is literally at the corner of one house away from my house. So
Okay.
I'm very close to it. I'm supposed to get really good speeds. And also, since I had DSL installed, I had this, I think they're called Aris modem, and it always made a very high pitch whining sound, like 10 to 15 kilohertz range. And some days it would drive me crazy. It's so annoying. It's just this whine in the background at a very high pitch. Um, and so I called AT&T, and T, and they organized to send a guy out the next day. Jumped through all the hoops and stuff, and signed waivers regarding COVID and all the other nonsense we have to do these days. The guy shows up on Wednesday and does a bunch of tests. Meanwhile, I'm trying to get work done, so I'm tethering from my phone, and and sure enough, the modem's fried.
Ah.
So he he gets a new modem out of the truck, and it's the much nicer, newer, upgraded version. I'm
Right.
like,
Right.
I'm so thankful. You know why? This old one made this high pitched whine that drove me crazy. Some days it would give me a headache. It was so annoying. And he said, "Oh, well, this is a faulty unit, and you were supposed to get a free replacement. These were basically." He's saying basically these are recall. And I'm like,
Right.
well, how come no one ever told me?
Because then
I
there'd
just
be
put
people
up
wanting recalled units.
I just put up with it for years. I searched online, I searched forums, I searched YouTube, I searched uh, the AT&T website. Could not find anything anywhere except for the odd person making a video with a microphone to show that it was making noise, and
What
no
What do you think it
explanation.
was? Was it the switching supply? Do you think, or what do you think
Well,
it was?
I actually had a look in it to see, because normally that is a switching supply that has a transformer or magnetic component that's not tightly wound enough, and
Right, right.
the
The
coils
laminations
vibrate.
are vibrating. Yeah.
And that's actually bad because over a long period of time, they'll actually wear off the enamel if
Right.
they vibrate too much. The wire enamel will come off and they'll start shorting out, and then the whole thing will die. But um, I found nothing like there were magnetics on the board for isolating the DSL line from the chip. Typical magnetics, just surface mount
Right.
part that are very compact and seem to be made of solid ferrite with wiring embedded in it. And
Right.
then there was one or two other inductors for voltage regulators, and they looked like they had the normal epoxy compound in them. And so I didn't see that I could do anything about it. And I could only imagine modern switching power supplies are typically resonant topologies because they're the most efficient and they're the least problematic for EMI, conducted and emitted. And those switching power supplies run at extremely high frequencies, often up around a megahertz. So I'm like, well, how could this possibly be causing an audible sound?
Noise?
So I wondered if it was something to do with the DSL line, or if there were two power supplies, one feeding into another, and they're both high frequency, but there's a beat frequency between them.
Right.
So if you
super heterodyne, basically.
Exactly, and if that's the only conclusion I could come to was that if you have two noisy things, but both of them are at very high frequencies, but they're kind of close to each other, then you get an audible beat frequency, which is the sum of the two. And that's like you say the old shortwave radios and AM radios. You'd tune them in and you'd hear this very faintly in the background, at least.
Oh, so it's even got a cyclic tone to it.
Yeah, well,
a cyclic component.
This one in my the DSL modem was it was constant, but it was just like this constant, but much higher frequency than that.
Yeah. Well, now cheap switchers run as low as 40 kilohertz, right? Would you say that?
Very poorly designed ones are
let's say older switchers.
Old switchers could be anywhere from 15 kilohertz to 50. There's a lot of basic switching power supplies from old computers, like 80s era. They didn't have the calculation software that enabled them to, and they also hadn't yet invented.
We didn't have the ferrite. We didn't have the materials as under control either.
That's right.
The inductors sucked compared to what you can get nowadays.
Yeah, they were more lossy.
More lossy, rolled off at high frequencies way quicker.
Yeah, Litz wire cost. They knew about it, but it cost a lot more to make then than it does now. For reducing copper losses. And so they had basic topology, which is fixed frequency variable pulse width, which is still the mainstay of switching power supplies. And anyone's first switcher design is going to be that kind of design, pretty much, unless you're using an application note from, what's that company called? Linear Tech. Who did they get acquired by? They got acquired by someone. Anyway, it doesn't matter. Linear Technology have all these parts and app notes. So you could get an off-the-shelf part that would do a resonant topology and really not know how it works or have to do any math. You just follow the app note and do what they tell you.
Right. Yeah, I'm looking at my... I'm trying to remember. They got purchased by Analog, didn't they? Analog Devices?
Yes, I think that's what it was. Linear Tech was acquired by Analog.
Yeah, so basically the two biggest analog, and TI was already bought out, or National, was already bought out. So it's like all the, we used to have this huge choice of analog sources, And now
Yep.
you just crack a linear tech book is about, is what you get,
Yeah,
or TI.
it's TI or analog devices. That's the way industry goes. But microchip are also one of the big ones on consolidation, and they've been acquiring a few smaller power and other analog ones like Microl.
Yeah. So I used to live, this is Precision Monolithics, PMI, and back in the 70s and 80s, this is why I designed out of to make load cell amplifiers. And look how much information comes with it. This is how I learned analog, was reading these things almost cover to cover.
Yeah.
And so this book is useless to me, and yet I don't want to throw it away just yet.
Was that back in the days when data sheets were honest?
Data sheets came in data books, yeah, because somebody once said...
And you paid for them. Like, you couldn't just get them for free.
Oh,
like
I got
now.
these for free, but I would tell the distributor to just pull up. They'd show up and their car would be riding low, and they would move their golf clubs and just unload all the data books on me. So I still have about 600 data books in here.
Well, they did that for you, Bill, because you worked for a company that was buying...
I worked for companies,
millions of
yeah.
parts.
Yeah.
But if you were just a standalone engineer inventing stuff like me, you had to pull teeth to get data books. I remember wanting to get Philips microcontroller data books for the MCS 51 and MCS 48 derivatives, 8051 and 8048 derivatives.
Right.
And this was in the 90s when this information started to become available online, but it was still very limited. I couldn't go to philips.com and download every data sheet. They hadn't migrated them all yet. All these companies needed to go through a massive republishing where they put it all in PDF. And the data I wanted was still sold in books, and you had to buy them from the distributor. The distributor, if you were buying millions of parts, they would give them to you. But I wasn't.
Right.
So. Yeah.
Right. Hang on a second. So here's a data book. It's missing its cover, but I bought it. Look where I bought it from. Radio Shack.
Yeah.
This is from 1973 or 2, and it is the National TTL data book back when they had pictures on the covers.
Yeah, it looks very well used.
It is, and it's written on parchment. You can see the paper's all brown and everything.
Yeah. I have books like that, which are my transistor lookup tables. All the standard transistor numbers.
Right.
And we would buy books from Dick Smith Electronics in Australia when it was still actually an electronics store. We all lament the acquisition of Dick Smith by Woolworths because we knew it was just going to turn to boring things, and it did. But they had, and I'm sure you bought them here, and Radio Shack had them as well, the transistor equivalency tables. And if you needed to replace a part, if you're troubleshooting, it was like the thing that was always on your desk. Oh, this obscure Japanese JFET is not available here, so yeah.
Yeah,
So
I have a 3-ring binder of all the transistor lookups. For example, you just saw the RCA series, right, where they would translate everything to an SK device.
Right. So if you SKs were made by Toshiba in Japan.
Yeah. Here, this was ECG series. Remember that? And so I was always translating to ECG.
Other than live streaming and novelty, do you ever refer to any of these anymore?
No. No. But because I use the internet, right?
Of course.
This was the internet back then. Matter of fact, it's even got the old dynamo tape thing on here to tell me which. And then I have another 3-ring binder full of line cards so that I knew who to go to for each different brand of things. So, but no, it's funny you mentioned that. I lived and died because I got my start as a kid. There was no maker movement or anything. I fixed things. And to fix things generally meant replacing a transistor, especially audio. And so, I would get my 2N3054s from Radio Shack for the outputs. Those were real common. But if I needed a Class A amplifier or something, I'd end up almost always getting an ECG part or an RCA SK part. I want to say SK3000. No, I'm not even going to say which one. But it's just been too many years. Yeah, that was the internet. And so you had to, part of the internet is not just the data, it's the indexing the data. In other words, your ability to search. So back then, you needed a good memory. I needed to know which of my dozens and dozens and hundreds of data books had the information in it. By the way, there's another national data book with a picture on the cover. But you had to remember where it was. So even when I went on vacation, I would load every nook in the car with data books. And on vacation, I would sit there and flip through the pages, just refreshing my memory as to where I've seen things before. Because it was all about going, that's in a Burr Brown book. Yeah.
What does that tell us when we go on vacation and read data sheets?
Oh, I loved it. It told me that I was self-taught and I worked my way into Commodore by doing stuff like that.
Yeah, you did.
Yeah, so I wanted to see what year this one was, and 1975 this one came out.
So it's 1 year younger than me, Bill. And not even, because I was born at the end of 74. Anyway.
Wow. Let's see what they're going on. They're talking in the chat room. They're talking about VCF is coming up in Wall, New Jersey, InfoH Sciences. Hey, Jeff, what's the date on that? Go ahead and post the date. By the way, we have a Discord channel, everybody. You can get to it by going to Coriolis-effect.com, and you'll see a Discord invite drop down. You can use that. So somebody else is talking about the old TI yellow books. Now I'm going to have to grab one.
I had some of those too. I had this really good one that was a collection of application notes for switching power supplies.
Oh, that'd be cool. Yeah, especially back in the day.
Yeah, mine were soft covers.
This is hardbound. Yeah.
I bought them in the 90s, but they were valuable because it was just one place where I had all the information I needed on all kinds of power supply design. And they started with the basic control theory and the basic math behind control theory and setting your poles and zeros for stability. And then they talked about the feedback elements in a power supply. And then they had app notes for linear regulators. And then it went all the way through to a 500 watt offline switching power supply. Wow. For 5 volts.
Right.
At some ridiculous current output, and the transformer design and everything. Really awesome resources. And now, of course, they have all of that still, but they have it put together in a PDF book.
Right.
And
right.
they have updated
and now you can go to places like Amazon, download an ebook as soon as your credit card clears, and you've got the data right there in front of you. Because they have great books on switching supplies, stuff we would have killed for in the old days, to have it all in one place.
Yeah.
So what do you got going here on this big donut-looking shape thing? Yes. What is that?
It's making me feel hungry. But anyone who's done any kind of radio would recognize that is the far field pattern of a basic infinitesimal or small dipole. And I was just firing this up. I happened to be doing this when we started talking today because I have a PCB antennas class coming up at PCB West, and I'm just updating. I've been using OpenEMS in the past for my classes because it's free open source FDTD solver that anyone can download and use, and it works with MATLAB or Octave as the main scripting interface, which is showing my age a bit that I prefer MATLAB because I used it in college. A lot more people now use would use something like Meep because it has a Python interface, and I'm not really a Python. I've played with Python a little bit, but I haven't given it the time to really get good at it. For now, I'm happy to stick with Octave and OpenEMS. But OpenEMS it uses the Visualization Toolkit, or VTK. And this program that you're looking at here is the VTK GUI called ParaView. And it's extremely hard to learn. It has too many features. And the reason for it is it can do anything. It's not just for electromagnetics, it's for any kind of scientific visualization and animation. And I really need to spend some time to dive into that and maybe actually do some dedicated tutorials on YouTube or something for using this for electromagnetics, because it's quite complicated because of all the options. But I can get it, at least the far-field pattern will be generated by OpenEMS through the Octave script and running OpenEMS from there. And as an output, it generates field patterns and other graphs you can generate as well. So I noticed that there was an update, a recent update to OpenEMS and a recent update to VTK, so I was updating it all and just running one of the basic examples to check that it works. So what that looks like, normally you start out here in Octave or MATLAB. This one's already generated these graphs, and they didn't come out too good, which probably doesn't matter, but I'll just show one of these examples. I've got the editor configured to be my Sublime text. So here's the infinite dipole script in MATLAB code. I don't know if you can read that text. I'm doing this on my 4K monitor, so forgive me. But basically, you just set it up. We're clearing the memory and everything. Physical constants is just loading an array for storing physical constants, and we have things like, drawing units, micrometers. We set up some basic paths and everything. This loading physical constants is a command that executes a separate script that comes with OpenEMS that loads up a bunch of things like the speed of light, the resistivity of copper, the dielectrics of various, dielectric properties of various materials, and so on, and we refer to those throughout the script. So we set up some geometry. We actually create a mesh. The basic geometry here is just a dipole, so it's just like a tiny, infinitely thin stick of perfect conductor, and that's just a very basic setup here. And then we create a mesh of the overall box that we're simulating within. We have to set a box, and we set up an excitation. So this, in other EMAG simulators, this would be called a port. You place a port, which is another little graphical element that has the property that it's a source of some kind of a certain theoretical impedance. So we set up a port as an excitation vector, and then we add that. We add the simulation box. So we set up the dipoles inside of a cube, a theoretical cube that has perfectly matched layer boundaries or things like that. That's what you use for FDTD, that absorb anything going out of the box. Your box could reflect or it could absorb. So normally, if you're simulating an antenna, you want to simulate it as if it's out in the universe with nothing around it, so nothing but vacuum. But we can't make it that big, so we have to give it a box, and then all the boundaries around the box are called perfectly matched layers, which just means there's a programmatic simulation trick that assumes that the edges of the box absorb 100% of any signal incident to them, or any wave incident to them.
Okay.
And then what's this? We do near field to far field contour is just something OpenEMS needs to set up to determine what's considered near field, what's considered far field. I may be slightly wrong on my explanation of that.
Do any of them talk about the Fresnel zone of between near field and far field?
It is mentioned in the documentation. Yeah.
Okay, just curious.
And with FDTD, you could if you wanted to simulate Fresnel effects, you could actually specifically do that.
Oh, okay.
I'd say if you and Fresnel phenomena is useful and used a lot in optics. I would even say if you wanted to simulate optics, electromagnetics for optical reasons, I would suggest MEEP is more set up, and their documentation is more geared towards optics. I think that the laboratory at MIT that created MEEP, which is another FDTD solver that's open source, I mentioned before it uses Python as a front end. That one, I think the lab that set it up is an optical science lab, not an electrical science lab.
Okay.
So all I've tried, they have some examples with antennas and basic things like this too, but I tried it out and it didn't seem very easy at all to learn how to drive it specifically for electronic or RF circuits or things like that. All their documentation seemed to be deeply geared towards postgraduate studies of and research of optics. So they were using a lot of language and terminology I didn't understand.
Okay.
But whereas OpenEMS is specifically for RF and microwave, and circuit board engineering. So it's much easier to follow and see what they're doing and understand what's going on, and then use it and modify things. So here we add the perfectly matched layer. Then there's a loop for post-processing the data, or for setting things up for post-processing. See this if not post-processing only, it just means we can set this variable here to do additional work when we simulate it for post-processing the results, and then adding additional outputs into the output folder, which we can then access to visualize things in a different way or get more data out of it. So then OpenEMS is actually, where is it executed? OpenEMS is, let's see. So all of this is set up, right?
Right.
I'm just trying to, init FDTD, and these, all of these write to an XML file that's basically handed as.
There's run OpenEMS about 20 lines below that.
Yeah, that's the one I'm looking for.
Yeah, it go just above the row of hash of stars. Line 75.
Yeah, this is it. So by setting that variable to 1, we're skipping the actual simulation and just running the post-processing as if we'd already done the simulation previously. But this is where, so all of that setup is done and written to an XML file using these commands. And that XML file is called sim.csx. That's the name of the variable that holds the XML file name. And that's passed to OpenEMS, and this command just executes the OpenEMS executable from disk, which is multi-threaded, multi-process. So it uses all your CPU cores and does a pretty decent job. So just to run a different one, here's an inverted F antenna.
Which is the one we see on PC boards a lot of times, especially
Yep.
for things like Bluetooth.
Yep. This is the basic structure you can see here, and these are the variable names. This is not a meandering inverted F antenna. It's just a basic straight radiator. That's it's got the meandering we do because it improves the omnidirectional field pattern. And it
Okay.
also allows the antenna to be physically shorter and use less board space. Whereas
And that's the reason I would have thought of is it's like loading a coil. It allows you to have a longer trace in the same amount of area, a longer antenna.
it allows you to have a longer antenna, but by meandering back and forth, the radiation happens in more directions.
Okay, less lobish then.
Yeah,
Not sure lobish is a word, but
but it's right. And even a dipole is very strong in a 360 degrees on one plane.
right.
But the
Hey,
moment you start to go under or over it, you lose signal strength, and that's not desirable for Bluetooth or Wi-Fi because you have a handheld device. You can't control the angle of it or where it's going to
right.
be. You don't want to wave it around and have it drop out. So meandering F antennas are popular for Wi-Fi and Bluetooth for
Right.
that reason that they are very, very much omnidirectional.
Right. Right.
Um,
Hey, can you explain what an infinitesimal dipole is?
it's a very short dipole it's a dipole that has a theoretically zero thickness of conductor.
Okay. Yeah, I saw that it's like less than a 50th of the wavelength is kind of
Or
where
it's
they call
well,
it,
yeah, and
which
very
would be
short. Yeah,
infinitesimally small. Yeah. And infinitesimal dipoles really aren't useful in the real world. They're useful for simulations and things, but in real life you wouldn't have an infinitesimal dipole. I'm
no,
thinking.
or you might have an array of them in some other
Mm,
type of
okay.
antenna, like uh, you'd have a tiny dipole array with a reflector on a ground plane underneath it to
Okay.
increase directionality.
So you would do it for a phased array or something like that.
Yes, yes.
Okay.
Um,
All right.
so how does this look? Well, let's go back to Octave. I'll run this real quick. Let's go double click on that script. Actually, just opens it. That's not what I want to do. I'm forgetting how to drive things. It's been too long.
Oh, wait till you get old, and your online dictionary goes offline, leaving just a little wisp of smoke. You know.
Oh yeah, right click run. I just realized I'm missing a toolbar here. There's supposed to be a toolbar above the file browser that lets you refresh or execute a script. It's on the right click menu, so I'll do it there. So it clears everything in the command window. It creates a new temporary folder. It creates the structure using that Octave script that we went through. And then it opens this other app that comes with OpenEMS that allows you to visualize it. So this is really just a tool for checking what you've written in the MATLAB code or Octave code
Right.
and visualizing it it's just a quick sanity check. Does this look real? But it also shows you, and this is one of the strengths of FDTD, it shows you the gridding into a voxel mesh. So this creates a 3D voxel mesh in the box, and you'll see that where the objects get smaller and more detail is needed, it actually increases the mesh density, or you could say reduces the size of each voxel layer so that you get more accurate simulation. So you can have variable sized mesh in FDTD simulation. So I can
Got it. Yeah.
I can exit this, or I could export this if I wanted to.
Now is the darker blue? Is that a ground plane covering up
The
part of the antenna?
the dark, the semi-transparent blue is the substrate, which is PCB material, FR4,
Okay.
and the teal color is ground plane.
Okay.
Now, with an antenna, especially PCB antenna, now with a wire antenna, you could do a dipole. You always have two conductors that are driven out of phase, or one of them is a reference for the other one to radiate from. And that's a very, very coarse way of saying it. But for a PCB antenna, you always need some kind of ground reference, which is established that you won't get radiation if you don't have a ground reference. That's like, this is the ground, and the antenna is the thing apart from the ground, and the two together create the radiation.
I used to hang around a radio station when I was young, and it was something like 5 kW effective radiated power. But we were near a river, which improved our ground coupling, and so we were measured as an effective radiated power equivalent to about 20 kW is my memory. So it was like not a magnitude, but it was huge amount more because of our ground coupling. And I just always remembered that meant that radio signals travel as much through the ground reference as they do through the airwaves.
Well, it's not even that so much as to cause radiation, you need charges to be moving, and they need to move in opposition to each other.
Right.
So in a dipole, you have a quarter wave, two quarter wave sticks end to end. So you have a whole half wave.
Half wave, right.
And you're moving charge out of one up to the other. So you're jiggling electrons up and down the post. But to do that, you have a drive point in the middle and a differential line, and you're pushing one stick positive while the other's getting pulled negative. And so the current of those is in phase, but the voltage is, well, this one's going positive, this one's going negative, and then it reverses and goes the other way. And you have to have that charge movement and current in order to radiate. And in a monopole antenna, it's a quarter wavelength stick.
Right.
But instead of having the other stick of the dipole, you have a ground plane.
Be the other half of the wave, right?
Because it has this reflective or mirror-like property. It gives you a virtual other opposing quarter wave stick. So you always have a radiator and a ground plane, and it's no different in a PCB. And in this case, we fold the radiator over, and part of the ground plane forms a reflective surface even that gives you a stronger signal in a certain direction. So let's exit that, and the script keeps running. And now you can see in our output folder, it's generating all these outputs. Here it is. So it's actually executing OpenEMS across multiple cores. And it has this kind of criteria where it keeps looping through the system until the energy in the system has dissipated below a certain level. And that can be a problem with FDTD algorithm. One of the drawbacks is if you don't have perfectly matched boundaries, or if you have a structure in your simulation that's very reflective and energy can keep going back and forth for a very long time or for forever, your simulation may never end. So you have to have something in your FDTD algorithm that says, you know what, this has been going too long, we're just going to stop.
Right. So in SPICE, it's like sometimes you don't converge. You just keep flip-flopping back and forth.
It's exactly the same issue, yeah. because energy can't leave the system because something hasn't been set up to be realistic.
Right. And you've accidentally invented perpetual motion.
Yeah, which only ever exists in simulation. So
Right.
this is the field pattern of the inverted F antenna. This is our what's this?
Oh,
This is feed
cool.
point impedance. So this is what you get with the post-processing code that's in the octave script. It'll take the outputs and then you can convert it into, you do inverse FFTs and things, and you get the frequency response or the reflection coefficient. This one here is the real and imaginary feed point impedance, and you can see the resonant point here is it's resonant right around the 2 point something gigahertz.
Is that resonant and anti-resonant, right? One after the other?
Uh,
the dip
yeah.
is that significant as well as the peak?
Well, it's the real and imaginary impedance.
Right. So what's the dash line?
Complex. That's the imaginary impedance.
Okay. So the imaginary impedance goes up and then it drops right after that, and then it levels back out.
So where that crossing point there is
right.
It's your resonant. It's the frequency of resonance. So that's where this antenna is most resonant, and that corresponds to the peak on the real part.
I gotcha. Okay.
So that's 300. That's close to the impedance of free space right there.
And this is with an open source program.
Yeah.
Yeah, this is cool.
And there's other examples. And this field plot, the plotting, I should be able to grab this and turn that around. So it's a 3D field plot. Unfortunately, what I don't like is it doesn't overlay the field plot transparently with the actual antenna geometry. Right. I want to see them both to really know, or at least see an XYZ coordinate marker. I've got to figure out how to add that to this in the octave scripting. I'm pretty sure it should be possible, but I'd like to see this overlaid with the actual geometry. But I can probably do that in VTK let's see if this one's loadable in VTK as well. Let me open. I go up one directory. I go IFA. Here it is, 3D pattern VTK. Let's hide that one and display this one. Yeah, so VTK shows me the XYZ axis. So because I know it's all keeping it the same XYZ, I can figure out from that what's my direction on the actual printed circuit board. So I just have to join those dots in my head. But this is pretty darn awesome for open source. Like, it's hard to use. I get it. You have to know but almost every electrical engineer, I think modern graduates, millennials.
They know some scripting. Yeah.
Millennials probably haven't. Most of them haven't used MATLAB. Most of them have probably switched over now to Python. So they might prefer using MEEP. But I don't see why someone couldn't write the exact same thing in Python for OpenEMS. It's just a command line executable that runs, and you pass it an XML file. Now, here's something interesting I discovered when I was fooling around with what's it called? Cook's Studio.
All right.
Cook's Studio, and we've mentioned this on a stream before, and I've played with Cook's Studio before on a stream. But look at this; it's got some octave stuff embedded in it. It even comes with GNU plot, and the octave executable, a version of that, is inside the installation of Cook's Studio. So obviously Cook's Studio is doing or has some capability to do some octave stuff behind the scenes. And I know that I haven't dived into it, but you can actually execute octave scripts as part of your simulation model in Cook's. But it also has, where is it? If I go into the binary directory and sort by type, look at this. It has openems.exe. And so
Wow. Okay.
there's one of the added things to Cook's Studio over the original Cook's project was that you can actually create a geometry of a circuit board RF or microwave structure, and you can do FDTD on it. It doesn't tell you what it's doing behind the scenes. It doesn't give you a command line or output, text output. It just takes ages. It gives you a status bar and takes ages and ages, and then it finishes and it gives you the graphs you want, like frequency response, S11, S parameters, whatever.
Right.
And it's actually using OpenEMS to do it behind the scenes. So
now, could you model a transmission? I'm assuming you could model a transmission line with this.
Yes.
Or, okay.
Yeah. So and actually, one of the first tutorials in the OpenEMS wiki is just a strip of copper that's a transmission line, and you put an exciter at one end, and you can actually generate an animation of the wave traveling down that piece of
cool. And so it does a true dual port, 2-port view of it, like you would see with a vector analyzer.
You can do it that way, or you can put usually there's a source and a perfectly matched layer bounding box, which is the simplest way to do it. So instead of having a source at each end, you can do a source at each end, which is how most of the professional grade RF simulation tools do it, like HFSS.
They do a port.
If it's an antenna, you have the port, one port for an antenna in HFSS. But if you're simulating a transmission line, you put a port at each end, and one of them is kind of used in your own mind. You use one as the from, and the other
the
as
origin.
the two. They're both ports and both emit power into the system to generate accurate wave responses. So, and you think about that, you have to have that in RF simulation, because that's how the software is able to simulate reflection.
Right. And so you could do 4 ports in and simulate crosstalk, then, I assume. Yes. Very cool.
Yeah.
So and this is in lieu of hugely expensive software. This software, ANSYS and software like that, Keynote, whatever, can be hugely expensive.
Yes, they are. But I will tell you this very confidently: I've used ANSYS.
They're better.
There's a reason why they're expensive. It's because they've invested huge amounts of money and time into building them to be excellent, and it's not just about being accurate. It's about being actually easy to use and very productive. And B, the number of people in the world who need software like this is a very small portion of the overall population. So the return on investment naturally has to be there. Now, I'm saying this looks like a replacement for HFSS. It doesn't even come close. I'll tell you that now. Don't be deluded. But if you just want to get started and experiment with PCB antennas, and you can't justify 100, I don't know how much,
20K,
huge amounts of money for a professional grade simulator. I mean, some of these, they used to have versions that were free for students and radio ham, licensed ham operators. I don't know if that's still the case. But if you can't, then this is not a bad way to start. You'll be frustrated. It's slow. It takes time and effort to set everything up, but it does work. And and it's for something that doesn't cost anything, that someone did in their spare time out of the goodness of their heart for all of us. It's actually pretty amazing what the results can be.
Right.
It's hard
Very
to
cool.
describe it. So yeah, that's what I've been.
That's
what I was.
One of the many things you've been working on.
Well, I haven't really. I mean, I just brought it up before we started streaming because I thought it would be interesting for us to talk about it.
Yeah. Oh, it was. I loved it.
Is
So,
any comments on any of this? Is anyone else? I'm just curious on the Discord. I don't have it open right this
so
second.
someone says ANSYS has a student license for electronic simulators, but it's quite limited. Ellie Fidesz said that.
Okay. Well, I'm not a student, so I can't get that. I know
Right.
that AWR, which used to be owned by National Instruments and they sold it off to Cadence, had a free version for licensed radio ham operators. And as I think as soon as Cadence acquired AWR, they nixed it. Because
Right.
I
Right.
went and had a look on the website and I could find no information about getting it for free as a licensed ham operator.
Right. And another comment was Mike Fikes had said, yeah, MATLAB and Octave can do complex matrices. That was at that time you were talking about the complex matrix interfaces and stuff.
Octave is extremely mature and powerful, and it is more than 80% compatible with MATLAB code. And there's even a whole lot of toolboxes that people have written for Octave that mirror MATLAB toolboxes. And some of those become a bit more divergent, but for the most part, it's extremely powerful. And if you ever used MATLAB in college, you can use Octave. But of course, if you're a professional engineer working for a company that has a tools budget, you could probably get the MATLAB.
Right. Right.
Yeah.
Right. So very cool. Well, thank you for showing all that. It's boy, that one drawing looks almost obscene the way it's facing us, though. Here,
Yeah, it's like a
there you
pinch.
go.
It's like a, what does it make me think of? Like those squishies we used to give away at trade show booths for stress relief, made of that closed
Right.
cell foam, and you just squish them real hard, and then they gradually open back out again.
Well, I would not have guessed that was the radiation pattern of a meandering F antenna. So that I learned something today about that.
Yeah, and the reason is that these nodes where there's basically zero signal is where either you're facing more into the ground plane
Right.
or
Right.
you're facing into the grounded end of the matching inductor portion of the F. The top of the F connects to the ground plane and forms a loop which gives an inductance that makes the antenna, the radiating arm, it makes it more resonant at the frequency that you want it at. So
Right.
yeah, makes it
Cool.
electrically longer, you could say.
So you were talking about Python, and I was going to say I have a story. Before we went live, I was talking about Terry Ryan, who wrote BASIC that was used in the Commodore 128. And Terry's background was he made BASIC be structured. He had loop while, loop until, do while, all these commands, and he got in trouble for doing it. The boss literally said, while it turns out you were right to include these commands, nonetheless, you went against my wishes, so therefore no big raise for you. So this is how life treats Terry Ryan, right? So I asked him one time about Python, because you mentioned Python and not really being a Python head yourself. I'm like, Terry, what do you think of Python? And he gets quiet. And he goes, white space has value, man. It's like, I'm like, what? He's like, it matters. You have to use a tab or a space. It means something. They used white spaces as syntax. And which is funny because he'd spent half his life making white space mean nothing at all, right?
Yeah.
And it reminded me of the old Cheech and Chong album where it's like he's kicking the piano, man. It's like it's white space means something. So
Yeah.
now
I think
I
that
set
would
my
trap me too.
yeah.
I would find that very frustrating.
Yeah. Well, the only time I had to use white space was, I started an ISP and ran it for 15 years, and I used SendMail. And SendMail, the syntax, literally needs a tab. If you have 5 spaces instead of a tab, it doesn't mean the same thing. And you had to go through when it didn't work, you had to go through and find out if something that didn't look like a tab was a tab or wasn't when it should have been. And it was like and you're using like VI editors and stuff. It just
Oh my God.
oh my God, yeah.
Pain.
Right. So, before. Oh, by the way, I got feedback from Anson Bow. He thanked us for talking about PCB Way for the contest that's being held there. For everybody that may not have seen last week, PCB Way is having a contest. Just Google PCB Way 4th contest is my advice. They
Prizes are really
have it
good.
linked.
They've got
What's
good,
that?
They've got good.
Oh, the
cash
prizes are great.
this time.
1,500, something like that.
Yeah.
So it's also this week I attended Dave Haney, if anybody's heard his name, of C128, but more people know him from the Amiga. He just celebrated his 60th birthday, and he was the youngest of the whole group of us. So the baby of the group just celebrated his 60th birthday. You'll find some pictures online of that. So, so we were talking. I've got my Commodore logo up here.
Yeah.
And my thought was to, because I'll be speaking October 9th at VCF East, and it's in the chat window, the address and everything from Jeff Brace, who's watching today. I was thinking about working on the presentation in bits and pieces and sharing it with you all here over the next month or two.
Yeah.
As a way so I don't just feel all the pressure at the last week to whip something out. That's a great idea,
and we get to be part of the in crowd who gets the sneaky previews of Phil's talk.
See that, right? So here's how I was going to start the talk, and I've started it this way. This is actually the existing one that's going to be edited. But, whenever we saw this logo ourselves, the very next thing somebody would do was this. We would dot the I, so to speak. We would, even on memos, on signs in the hallway, anything, we were always adding little eyeballs to our Commodore logo.
With the chicken head.
There's a name for this. It's called Chicken Lips. That's the official name for this in the old days. And of course, Commodore's not around anymore, and the proof is that everybody thinks Apple invented the home computer.
Oh my gosh.
And when you see a documentary on the 80s, inevitably they'll show an Apple. They won't show an IBM. They won't show a Commodore.
The first home computer was the Altair, officially.
Well, that was cool in War Games. When they showed an Altair in War Games, I was, woo, Altair. Yeah, that was probably one of the best cameos.
Had to be now, I'm not against Intel, but the Intel 8080 was a good processor. The 808-6 family, not a fan. Yeah. I know they had good reasons to have.
I was a fan of the 8186. I thought that was a bitchin' little microcontroller-ish thing. It wasn't really a microcontroller, but it had enough stuff. It had chip selects and wait state programmable. And wait states were a big thing. It always meant in the old days you had to add some kind of stateful logic if you were trying to use just an 8086. You had to go, all right, that's been 3 clocks. Let loose the wait line, the ready line, wait line. It's bar wait, I think it was. So I did like the 186.
What's it called? The segmented addressing just.
Oh yeah.
I know they had good reasons for it, but architecturally painful.
And yet you ended up adding a chip to act as your IRQ controller. So it's like, just take this chip and half a dozen to a dozen other chips just to get the core going. And the 8186 came along and said, well, you know what, at least add ROM and RAM and a couple things and you can make it work, reset and clock and stuff. So what I was going to say, though, is the Commodore did do a cameo on Wonder Woman 84, and they actually showed it in context of how it would have been used. They showed it in kind of more of a scientific setting. So, and that's how pets were used. That's what they showed. They showed a bee machine, I think, which was a grown-up pet, is kind of how we thought of it. That there is a type of pet behind me called a 2001. I was going to drag this up to VCF with me because I'm thinking this year maybe I'll just talk about Commodore starting with the pet and walking from VIC-20 to C64 to the TED series to the 128. I can't go further because that's after my time. I don't literally have any Amigas here, so I was going to do that. But in keeping with this, oh, by the way, I was watching Marvel movie outtakes, and there was that scene where they tell Dr. Banner where he said, "Hey, you'll like it, Doc. We have all the toys." And in the outtake, or in the unused scene, he says, "What, like a Commodore 64?" So the Commodore 64 almost made it into the Marvel movies, but it didn't.
I love it.
And the reason why it didn't is because Commodore is not around anymore. The chicken has died, as we say.
The chicken can no longer sponsor the movie. I love that with the Plus, though. That's funny.
Yeah. Well, I had somebody tell me, he literally screamed on the chat channel. He's like, I can't unsee that now that I've seen it, the Commodore logo. So, well, we're come up to the top of the hour. I just wanted to explain why I had this Commodore logo here. I've got more shot. Ooh, here's one. I was actually going to show from my trip inside of MOS that I took 3 years ago. Actually longer now.
It looks very dangerous in there, and leaks everywhere and water and
yeah, it was cool. Little campfires and stuff. Yeah,
bad chemicals.
Stalactites. Yeah, there were calcium stalagmites sitting right next to where somebody had gone to the bathroom. It was pretty wicked. So excellent. Well, Ben, my friend, it was great learning about these open source tools. I love it. I wish my brain worked well enough that I could just sit down and emulate what you just showed us today. But I know I wouldn't be able to.
This is just one of the scripts, like the author of OpenEMS, Thorsten Liebig, is a lecturer at one of the universities in Germany. This is just one of his own examples he put together. So you could do what I just did pretty easily. I put almost no effort into this. Like I said, I just opened it up before we started because I'd updated the software and I wanted to test it, see if the update broke anything. But yeah.
Yeah. Cool.
All fun. And
yeah. So once again, we didn't talk about bootstrapping JFETs, but we were ready. So that might be what we talk about next week.
Right on.
So, all right, Ben, my friend, we'll see you around. We'll see everybody here next week, and have fun computing.
Yeah, have a great weekend.
See everybody.
And happy Labor Day.
Good holiday, yes.
Those who are having the day off in the United States. And for everyone else, I hope you get a nice public holiday soon too.